And that is just plugging in whatever points you feel like and trying to piece together what the entire function looks like based on whatever points you have. Because do you really have any effective way of connecting the dots? Well, perhaps not until you've plotted a whole lot of points and it gets quite tedious. If you have at least some curves, especially curves of a format you recognize, like a circle or a parabola or an ellipse, that can put you on the path a little faster to seeing, to visualizing the entire function, or the entire graph. Now, another thing to keep in mind, of course, in trying to visualize a function, if there are certain things you know about what inputs it could take and what outputs it could take, or maybe won't, then you can ignore selected parts of your space right there. So it's important to be able to get an idea as to what the possible inputs, possible outputs are. What is the domain and range? Is it something that only assumes positive values? Are the inputs restricted to a certain interval? If you know that, that can be very helpful. So supposed to do this function. Now, what's the domain of this function? Well, before we try to answer that, we have a log here. What's the domain of log? So whatever we put here has to be strictly positive. So x squared minus y squared must be positive. So what does that say about how x and y relate to one another? Right, we have this, but can we simplify this a little bit? So we have x squared greater than y squared, and then if we take the square root of both sides, so the absolute value of x must be strictly greater than the absolute value of y. So that means, take a look at, for instance, here, where y is equal to 1. So along this line, where y is equal to 1, then x, only these x values are allowed. So here we have x less than minus 1, x is greater than 1. So if we extrapolate, so here's where y is equal to 2, then even more of a domain on x. So what's happening here is this portion of the xy plane is excluded. There will be no values of a function there, because you'll be taking the natural log of a negative number. So to visualize this from above, in a situation like this, where only the domain outside of these lines is excluded. And the lines themselves, those are not included either. That's where you'd be taking the natural log of 0. And I've only taken care of the upper half, similar thing down below, with the absolute value of x greater than the absolute value of y. So we only have values of a function here and here. I want to mention one other technique that, if you use in conjunction with level sets, can be helpful. It's called the method of sections. So you have z being a function of x, y. So I'm specializing, much of a discussion, especially the early part of the course, will be about functions of just two variables. What we do is we take the graph of this function and we restrict it, only a portion of the graph, or portions, that are contained in what I'll call vertical planes. An example of a vertical plane would be, for instance, the xz plane, where y is equal to 0. So that's the xz plane. Or where x is equal to 0. That's the yz plane. So we have a plane passing through here and through here. So I'm not including the xy plane, that is a horizontal plane, because it's z being a function of xy that we want to plot. I'll just draw a portion of these planes so you can see the yz plane, and here this is a portion of the xz plane. So what we can do is just focus on the portions of a graph in those planes, and it's relatively easy to get a hold of those portions because they involve setting y equals 0 or x equals 0 in the formula for the function. Now, these are not the only sections you could take. You could try something else where, for instance, take the plane where y is equal to x. So this would be coming out of the board in this direction. So it would contain the line y equals x. So now, let's take both concepts, level sets and sections, and apply them to a function. See what it tells us about its graph. So a function we're going to look at is z is equal to x squared plus y to the 4th. So its domain is the set of all real numbers. Its range will be a set of all non-negative real numbers. Now, suppose we take a look at level curves. So x squared plus y to the 4th is equal to k. Now, to try to get an idea as to what values x and y are going to satisfy an equation like that for whatever k we choose, there's different ways we can go about it, but one thing we could do is solve for y plus or minus k minus x squared. So this tells us for a particular k, so if k is some fixed z value that we're choosing, so we need to figure out, first of all, what x values are even in play. What x's are going to be allowed? So we need k minus x squared must be greater than or equal to 0, k is greater than or equal to x squared, so the absolute value of x must be less than or equal to the square root of k. In other words, x between plus minus. So for any k that we choose, x is going to be limited to those values. Y, on the other hand, this is at its smallest when x is equal to the square root of k, then y is going to turn out to be 0. But if we let x equal 0, we get plus or minus the 4th root of k. So this is a possible range of values that y can assume. What we could do, you could whip out one of those infernal graphing calculators. show your work or your toast. So what I've done, and this is one of the figures in the notes, shows some level curves for various values of k, put the origin in the middle. So because x is limited to plus or minus the square root of k, but y is limited to plus or minus the fourth root of k, which is going to be smaller as once k exceeds 1, then what we have are these, it's kind of like taking some sort of oval or maybe a racetrack type shape and mushing it from above and below. So for instance here we would have, this is for k equal 1, k equal 4, k equal 9. I chose values of k that were perfect squares in the figure just for convenience. So what happens is, as z increases, we get some kind of odd bowl shape, but bowl is stretched out along the direction of the positive and negative x-axis compared to the y. We'd like to have a little more information before we actually try to graph a function as a whole. So for that, we're going to use the method of sections. We're going to take this function and we're going to plug in x equals 0, see what we get. We're going to plug in y equals 0. So first, if we take a look at the section in the xz plane, where y is equal to 0, so that means that z is going to be x squared. So we're going to get familiar parabola, something like this. On the other hand, in the yz plane, where x is equal to 0, we get z is equal to y to the fourth. So when we include that, it's going to be stretched out. So what happens is, if we take a look at just viewing in the xy plane, x squared, as opposed to x to the fourth. So what we see here is that x to the fourth, it starts out being a little bit flatter near the origin, but then once it gets past, this really is going to be a z value of 1, it's going to really take off. So now, using these sections, and then between that and the level curves, we can start filling in the rest of the graph in sort of a grid-like fashion. So this will, to some extent anyway, convey the shape of the entire thing, taking a lot less work than just plugging in various points when you don't really know what to expect as far as how you would connect them. This is one thing you can do, is plot a few level curves for whatever values of k, and then plot some sections. So now, between the two of them, you can start to piece together the entire shape. We have one other that'll do. Z is equal to natural log of y minus x. So for level curves, what we'll do is set natural log of y minus x equal to some fixed z value k, and then we want to be able to rearrange it so we can just write y as a function of x or x as a function of y, whichever one turns out to be more convenient. So in this case, it's going to be actually quite convenient to express y as a function of x, because what can we do with that? Take e to both sides, so we get y is equal to e to the x plus k. So now we can go ahead and plot level curves. The nice thing about this is, once we plot just one of them for one value of z, so one value of k really, then it's going to be quite easy to get some more of them. So for instance, when k is equal to 0, then we're just going to have e to the x. So now if we want to get level curves from more values of k, how are we going to get them, their graphs, from the graphs of this? So here is for k equals 0, it shifts to the left. When you add to x, it's to the left. X minus k shifts to the right. When you add to y, it goes up. You subtract from y, it shifts down. Okay, so we're just going to shift these to the left, at least for positive values of k, and so on. So k equal 1, k equal 2, so on. And then we can also consider negative values of k, that's fine too. And then we'd have shifts to the right. Alright, so now we have some level curves to work with. So what we see is, as z increases, as we're looking down on the xy plane, that means these curves keep shifting, not just to the left, but to the left and up at us, because this corresponds to higher and higher values of z. But let's take a look at sections as well. So now, we can plug in, so for the xz plane, yz plane, that's y equals 0, x equals 0. What happens when we try the xz plane? Plug in y equals 0. What sort of curve do we get? We plug in y equals 0 over here. It does not exist. Why? Right, or we even go back to the original formula. Natural log is undefined when y is equal to 0, so nothing. And then, when x is equal to 0, z is equal to natural log of y. So we have a function whose graph never touches the xz plane. So we'll fill in what we have in the yz plane at least. Z is equal to natural log of y. So y is required to be positive. So what happens is, here, think of a half space that's in front of the xz plane, so in this direction, that's where the graph lies. Behind the xz plane, there's nothing back there. So nothing in this half space. That's back behind here. So now we have z equal natural log of y. So we have all possible values of z and only positive values of y. A nice slowly growing logarithmic function. So this curve gives you an idea of how to place these graphs. So when k is equal to 0, we have level curve corresponding to the exponential function here. So this is y is equal to e to the x, and z is equal to 0. So that's what's sitting in the xy plane. And all of these shifts of the graph of the exponential function have to, so it's like we're taking all these strings, if you will, represent these that are shaped like a graph of an exponential function, and we're tying them on to this curve. So we get something like this. And that represents roughly the graph of a whole function. Z is equal to natural log of y minus x. So I'd highly recommend trying this approach in order to graph functions of two variables.